All right, this is the test review for the Unit 3.1 3.2 test on circles. Questions 1 through 5 in part 1 are matching vocab questions. So if we take a look at this picture, we are first asked to pick a chord. And remember, we said that a chord is a segment, not a line. So it's a segment that intersects the circle in two places. So if you look at your choices are AB, which is not a chord, line L, which is not a chord because it's a line, line M, which is not a chord because it's a line. Then we have BC or DE. So both BC and DE are chords. The best answer here is going to be DE. So we pick choice E here. And the reason for that is that you were also asked in question 5 to find a diameter. And BC is the diameter. And it's the only one from this list that's a diameter. All right, remember a tangent is a line that goes that touches the circle in one place. So if you look at your choices, the line that touches the circle in one place is line L. And that one place, remember, is called the point of tangency. So this is your tangent. Your radius is going to be the segment from the center of the circle to the side. So you're given 2 radii, but only one is a choice, and that's choice A. That's your radius. Remember, the secant is also a line, and the secant intersects the circle in exactly 2 places. So if you look at the line M, we see that that goes through the circle in exactly 2 places. So that is your choice C there. Okay, moving on to part 2. You're asked to find the value of x or y, and it also says that segments that appear to be tangent are tangent. So in number 11, segment BC appears to be tangent to the circle. We're going to assume based on the statement it is, and that's important because that means that this is a right angle. So from the radius to that tangent segment is a right angle. All right, so we can use the Pythagorean theorem. I kind of like to resketch my triangle here. I know I drew it a little differently. So if this is x from A to B, and from B to C is 30, and be careful here because from A to C is not 18. There's this point D in here. So if I look at this, from A to D is also x, because AB and AD, both those segments are radii. So I could call this x plus 18. All right, so we plug this into the Pythagorean theorem. A squared plus B squared is C squared. So my legs, A and B, are x and 30. And then C squared is my hypotenuse squared. All right, so this becomes x squared still. 30 squared is 900. And then this you actually have to FOIL. So you actually have to multiply x plus 18 times x plus 18. All right, so you remember this from Algebra 1. First terms, x squared. Outer terms, 18x. Inner terms, 18x. Last terms, I'm pretty sure that is 324. And then remember, we can combine those middle terms. So we get x squared plus 36x plus 324 on the right, and we still have x squared plus 900 on the left. So we can subtract x squared from both sides. I could subtract 324 from both sides. So let's see, 900, we get 600, then 670, 576, I think. 576 is x squared, and then we could take the square root of that. So it would probably be helpful to have your calculator, which I have. Mine's just down below. The square root of 576 is 24. All right, so when we get to the statement that x squared equals 576, take the square root of both sides, x is 24. All right. All right, in problem 12, again, we said segments that appear to be tangent are tangent, and we said if there are two tangent segments that come from the same external point, so point G, they're congruent. So this is a much easier problem. If GH, if that segment is congruent to segment GI, that just means that their lengths are equal. So 2x is equal to x plus 12. All right, so we could subtract x from both sides, and we're left with x equals 12. It's nice when we have easy problems like that, huh? All right, last but not least, in problem 13, we have the problem where we're trying to find y, and we've got to put a couple ideas together. There's no tangents here, first of all, but we do have an angle that is inscribed in the circle, and it's actually, if you cover this, inscribed in a semicircle. So if I look at this semicircle, this angle is inscribed in it. So something we learned is that any angle inscribed in a semicircle has to be a right angle. And we know that's because the inscribed angle, in this case 90, is half of the angle of the arc, which would have to be 180 if that's a semicircle. So we know this is a right angle. We also are told that these sides are congruent. So I know this is an isosceles right triangle, which makes it a 45, 45, 90 triangle. So I know that the expression 4y minus 7 has to be equal to 45. And now we can just solve by adding 7 to both sides. So 4y is equal to 45 plus 7, which is what, 52? Is that right? I'm not so good at doing math in my head. Then we would divide 52 by 4. So 52 divided by 4 is 13. So divide both sides by 4, y equals 13. All right, last question on the front. Let's see if we can make it through. The cruising altitude of a commercial airplane is about 9,000 meters. Use the diagram to find length AB, the distance from the airplane cruising at, an airplane at cruising altitude to Earth's horizon, and round to the nearest kilometer. So the first thing I would do, because we're going to be working in kilometers, this picture, the radius of the Earth is drawn in kilometers, I would probably change 900 meters to kilometers. So in another class prior to this one, probably a science class, you learned about metric conversions, maybe in middle school math. So we have kilo, hecto, deca, your units, and then you would have deci, centi, milli. And sometimes you learn King Henry died drinking chocolate milk. Okay, so if I have 9,000 meters, meters being my units, if I line this up, I have 9,000 meters. If I think about what is that in kilometers, that's just going to be 9 kilometers. So 9,000 meters is equal to 9 kilometers. Okay, so when we go to label this diagram, let's use it in kilometers, not meters. So they tell us the cruising altitude was 9,000 meters, so that's going to be your 9 kilometers. So if you look at this picture, the distance from the circle to A, that's your 9 kilometers. Because if you're below that point, you're in the Earth. And we don't want a plane to be in the Earth. That would not be very good.
Did she leave?
Yeah, she was down here a second ago. I don't know if she left, but she was just down here. Sorry about that. It's my office mate. Her kids were looking for her. All right, so now if you look at the diagram, we already know the radius of the Earth. So 6,371 kilometers would be from C to that point. And then what we're trying to find is this distance from A to B. I'm going to call that X. All right, so if we redraw this triangle, I'm just going to draw it over here. This is obviously not to scale. We're trying to find this long leg X. We know this short leg is 6,371 kilometers, and the hypotenuse is going to be 6,371 plus 9, so 6,380 kilometers. All right. All of that, like figuring out how to label this, that's the hard part. The rest is just the Pythagorean theorem. So since we have the hypotenuse, we subtract the squares to find x squared. So we're going to do 6,380 squared minus 6,371 squared equals x squared. All right, so plug those into the calculator. 6,380 squared is, oh, that's a big number. You know what? I'm just going to do this in the calculator. So I can do, your calculator can do this whole thing for you. So 6,380 squared minus 6,371 squared. Our difference of squares is this number. So that's 114,759. Take the square root. X is approximately 338.76. Or 761. So 338.761 kilometers. All right, so that is the distance from where the plane is to Earth's horizon.